Hello everybody and welcome to Tel's Bench. So today's video is all about using the GPIO pins on the Agon Light 2. So what we're going to do today is take a look first of all at the processor itself, and then we're going to put together some examples of how you can make use of the pins. If we take a look at this 100 pin device, which is the EZ80 that's been fitted into the Agon Light 2, you'll see that there are three sets of 8 pin ports. You've got port B, port C and port D. Follows like an alphabet, right? Makes sense. And some of these pins have got alternate decals associated with them, which we'll get to at some later point. So we're going to be using port C to do these examples with. So much like an Arduino, these pins can have different functions. So we've got 0 to 7 there. And if I rotate the image 90 degrees clockwise, you can see here it's exactly the same thing for port B and port C. So let me just put that back anti-clockwise. I've invented a new word, anti-clockwise. Yeah, so I just took this basic information from the user manual and just removed all the unnecessary stuff and put a massive EZ80 in there so it was clear what this was about. So what we're going to do is we're going to look at the different modes and then we'll work through those in examples. Many of them we will. Some of them are quite difficult to emulate, so we might miss some of them out, but we'll do all the basics. And for the most part of this video, we'll be using BBC Basic because it's the sort of lowest common denominator, if you like. Well, actually, it's not really the lowest common denominator at all, but it's the one everybody can use. Not everybody could use assembler embedded or, in some other kind of assembler and port it over. If you're an assembler coder, you'll also be able to do the same things in BBC Basic, but not the other way around. That's why I chose that. I might actually use some assembler in some of the things for the interrupts, but let's see. GPIO modes 1 and 2. Alright then, pin modes. Let's take a look at the product specification from Zilog, which is what I said we'd do. So let's go and find the table of contents and find there is general purpose input output. So, right, I'm just looking at this. This is just what I've told you in the intro. Basically, 3 8-bit ports. All the pins can be either input or output, or they can be used for interrupt purposes. So, for example, on a leading or a falling edge, or either, if you wanted to monitor what was happening on a particular line, you could make it go to a service routine for that. And then the operation is there are 4 port register itself. So that's the register that you're actually reading from, or you're putting data to, presenting it to. The data direction register, literally that, it's whether it's going out or coming in. And this is some alternate information which allows us to specify, or them to specify, more alternatives on how these are used. We can skip that because we've already been through this. But basically, I've just explained to you that. So this X means what is the port. So you can replace this X with whatever port we're working on. In this case, we're going to be looking at port C. So this is a standard output. So this is in mode 1, and this is an output mode. So it's much the same as it would be in an Arduino. You can either output a 0 if the port register bit 7 is 0, or you can output a 1. Right? It's still an output, but it's either an output of 0 or an output of 1. Yeah, so that's that. And then here we have mode 2, which is standard input from pin. In both of these cases, the input is high impedance, and it responds to what you present, what voltage you present on the input. Just be aware there are no internal pull-up resistors like Arduino. The only difference is I think the Arduino, correct me if I'm wrong, but I think the Arduino has got this the other way around. The DDR on the data direction register, I think on the Arduino, 1 is an output and 0 is an input, but this is the exact polar opposite of that. And then there are some variations on there. So if we just go down here. So mode 1, this port is configured as a standard digital output pin, which is what I've just said. And mode 2, the port is configured as a standard digital input pin. The output is tri-stated high impedance, and the value stored in the data register produces no effect. As in all modes, a read from the port return the pin's value. Right. So these are pretty much almost exactly the same way as an Arduino does it. These ports for this sort of standard input and output will only allow you to, I think, drain or source 8 milliamps. So it's much less power available to you in terms of the current draw than it is on an Arduino. I mean, on an Arduino, I think you can go up to sort of maximum of 40 milliamps or something ridiculous like that. I can't remember off the top of my head, but certainly 20 is quite common for some things. People drive speakers with it and all sorts. So yeah, that's these two. So what I'd like to do is to just concentrate on mode 1 and 2 first. We'll go and do some experiments, and then we'll come back to this and we'll continue with it. So that's what we're going to do now. Okay then, so we're going to go through the modes, starting in mode 1. So notice that these two alternate bits there, which form part of the mode selection, are both set to 0, but the mode is listed as being 1. What I've done in my examples is write them out for the mode numbers. So the mode number M1 really refers to this group here in mode 1. But the actual value that we're going to put in is going to be 0. And I'll show you what I mean. So let's load M1 first. And that's going to be the output we're going to do. .txt. Let's CLS that, list it so we can just take you through. First of all, we're setting the, ignore this bit of that, it's just clearing the screen. So here we're setting Alt 0 and Alt 1 for port C to 0 to make sure we're in the right mode. And then what we're doing here determines whether it's going to be an input or an output and which bit is affected. Then we actually set this variable here, which is PC underscore DR, so that's port C data register. That's where we actually apply our data to in order to send it out on those GPIO pins, is 9E, and the data direction register for port C is going to be 9F, and this information is all in this document here. And then we just go and put 0 out onto the PC DDR. That means all 8 bits in port C are going to be output pins. And then if it's going to be a 0 presented to it, it's going to be a 0 coming out. And if it's a 1, it'll be a 1 coming out. Then on the proc display test, it really is just a little proc there that just tells us what we're doing. GPI mode 1, PC up to PC7, and it's an LED chaser. What you'll see is just like Knight Rider. These should be streaming across here and then back again. This little board I made up is a 10-pin LED. You got 10 current limiting resistors, 10 wires to connect them in, and then these wires, which are out of an Arduino kit I had, are all connected to port C. So here is pin 17, which is on the top, and that's bit 0, and below it I think it's a brown one, that's bit 1, and then you come up to pin 2, and then below it's pin 3, and so on. This is just a standard 40-pin IDC connector. If you've got any old drives at home, floppy drives that is, that use a 40-pin cable that you're not using anymore, you can use that, or you can use these Arduino wires, which is what I used. So the idea is if we put a positive voltage of 3.3 on the pin, the LED will light up. And okay, so we've got start playing the main loop. So we've got the repeat loop till false, that's everlasting. Then we call proc chase leads, and then it starts from 0 and goes to 7 with an increment of 1. And then we chase leads again in the opposite direction from bit 8, which is 7, back to 0 with a -1 increment. So that's the idea. The chase leads you're sending at the start bit, the end bit, the increment, and it's just a standard for loop. We have t equals time, so that's the clock value off the board. And then we go in and put to the power of x, 2 to the power of x, into the register, so the light will shine the first one in. Print the same thing, so you see the value on the screen at tab 0, y5. And then we repeat until, basically repeat this little loop here on this single line until time is incremented by a count of 20. And then it will go next X, and then it will go through, it will increment X, and X will be a higher order value, and stream them across there. So let's just run it. Let's just run it. And as you can see, we've got a nice little Knight Rider array of LEDs. As you can see, this is a nice count there, which is 2 to the power of X, which allows a single LED to shoot across. So that is it, really. It's as simple as that. Originally, I was going to use port D, but then I realised, although you've got all those ports available to you on the EZ80, they're not really all available to you. And actually, if you look at the pinouts from this in the user manual for the OLIMEX Agon Light 2, you'll find that most of the GPIO pins that you're going to be able to or want to use are going to be on port C, but you can see that there's other pins on there. But that's what I chose to use. So the next one we want to load is M2, and that's going to be input.txt. Right, now let's have a look at the listing on this. We're saying that the DDR register for port C is going to be all ones. That means all of them are inputs. Right, okay, so we proc displayed the test and we're saying this is pin mode 2, import C, pin 0, ground pin to test. So we'll only do one of these, and that's going to be this one. So I'll take this one off here, this orange one, which is pin 0, and I'll attach a wire to it. I will see what value comes up on the screen, because in the repeat loop, okay, I've just noticed here, by the way, this says on 70 in the main loop, which is repeat forever. We've got this srem s get equals pcdr. That is old code, so just ignore it. I will take it out for the code that's linked to. But we're just setting t to time again, and then we're going into the inner loop, which says, right, print at this tab location, get the pcdr, right, the data register, and AND it with 0, 1. Well, we do that because we need to ignore all the other bits. We're only interested in bit 0. So if bit 0 is 1, then you'll get a 1 out. If bit 0 is 0, you get a 0 out. And then we've got a little bit bigger time loop there because we're not chasing anything. And that's it, really. So what I'll do now is I'll remove the orange pin, or connector rather, and I'll plug in another one in its place. I'll just keep that way away from anything metal. CLS, I'll run it. Alright, and you'll see there that it's showing 1. That is the output. So what I'm going to do here, which looks dangerous but it's not, I'm going to see where it's pointing. That is the USB casing, which is ground. Now if you just watch, well actually I can just do it on here, can't I? On the USB. Right, can you see the screen there? It's gone to 0. I'll take it off. It goes to 1. Put it down. It's 0. Take it off. It's 1. Down. It's 0. Okay. So that's in standard pin mode, if you like. If we look a little bit down there, that's input from the pin. The inputs are high impedance, and whatever you present on the pin will be, from the outside, will be reflected in what you're seeing coming back. Yeah, these ones we'll come on to in a minute, but I just wanted to show you what I've done and let you know it's not actually that difficult, really. It took longer to do actually than I thought, because this was a bit of a pain, this little board, because of all these little resistors. I hate these. I wish I had a resistor pack. It would have been much easier. These are these 8 watt resistors you get in the packs. They don't really fit in the breadboard holes. They need to be thicker legs. So I end up doubling up the legs and squeezing 2 in the one hole. It just took me a while to do that. And then I had to write a little bit of code, of course, for this, which wasn't really too bad. So yeah, let's go and have a look at the next bit. GPIO pins, modes 3 and 4. So we've done modes 1 and 2, and I said that we were going to have a look at some of the other modes. So we'll look at 3 and 4. Basically, they complement each other, really. These are open drain, so what that means is, if I go down a little bit, an open drain means that this basically is switched off, right? That's not turned on at all. you won't get a power source out of it unless you strap a resistor from there to VDD. Right, so it's for you to do. It depends on what interface you're going to, whether you need this or not. And the other one would be open source, and the source is, well, it should say VSS really down there. I guess it says ground, but that's the same thing. So that if you don't know, the drain and the source is where the electrons come from, and they travel in this direction to the drain. That's where they get their names from. Anyway, that's another story. Let's go back to here. In mode 3, you won't get any voltage. If you put a 0 out, you'll get a 0, right? Because the source is working. It's not an open source, it's an open drain. So it means when that bottom one is turned on to give you a low, you will get 0 volts. But unless you do something with a resistor, pull-up resistor, you won't get the plus 3.3 volts. So that's what we have to do. So here, look at the breadboard in the top right-hand corner of the screen. I've got this little alternate use of the breadboard that you saw a little while ago, and I've got a little blue LED there. So if you follow that, that goes to port C, bit 0 on pin 17, and it comes directly to the LED. Because in this case, we're not driving any power out of it, we're just attaching to it. And currently, this resistor, which is the pull-up resistor, is just hanging loose. And here we've got 3.3 volts coming into the top. So on this side, if I do a list, what I've done is something slightly different, but I've put the value of A0, which is the alternate register 0, or Alt 1 as they call it, a bit confusing there, to a 1. So that means we're in open drain mode. Everything else in terms of registers stay the same. We go and tell you what we're actually doing. GPI mode 3 open drain, 0 volts output, and PC 0 LED. Right, that's what we're doing. Okay, and then it just prints out these registers. And then in a repeating loop, what we're going to do is we're going to put 0 out. So you'd expect that normally to be high, and then we're going to have a little delay, and then we're going to put out into the data register a 1, and then we're going to have a little delay again. And so if we were doing this in mode 0, this should really work with a resistor through here and turn the LED on. So what I'm going to do is just run this, and what you'll find is the LED doesn't come on. And that's because there's no pull-up resistor. So if we put a pull-up resistor in, you'll see it's now flashing. We've got a little oscillator basically. I just put in 2 states out, generated a little square wave. I could show you on the scope, but it just means changing all the camera setup again. But it is working correctly. What I'm going to do is I'm just going to move this window out of the way because it's quite distracted. So mode 4 is the exact opposite of that, right? So it means that the top one is turning on, the drain, and the source is not, right? It's an open source. So it then refers to an external pull-down resistor to connect the supply pin to ground. I can't quite think when you'd want to do that, but you might want to do it for some reason. So I'm not going to go and do mode 4 because mode 4 is the exact polar opposite to mode 3. So as you've already seen it, and you know we've explained it, we've talked about it, there's no point in doing it. And then we've got mode 5, which is basically reserved, right? And all it means is it's a high impedance out, but it will do nothing for you. And all of the other modes, I think I mentioned it earlier, it's the same thing, but what you're doing is doing it on an edge or a level. So if it's on a rising edge of a pulse as it starts to ascend, I don't know what the value is for that, but it'll be something over 0, right? It's probably going to be like 0.7 of a volt, I'm guessing, to say, you know, anything above that, it's on its way up. Not quite sure how it measures that it's going on its way up, or just the level of that, I don't know. But that's what it's doing. And also you can do it both edges, so if it's going up or going down. And you can also do some other clever stuff here with, you've got a level sensitive one on 8, and then you've got single edge triggered interrupts. I'm not sure about the value of doing this in this video, so I think I'm probably going to leave the interrupts out at the moment because it would take quite a lot of work, and I'm not sure what the reception to this video is going to be at the moment. So I've decided to call it at mode 5, which is halfway up, and it's all the ones that most people will use, at least most amateurs, and the people who are looking to write higher level stuff on the GPIO specific interfaces to a particular chip or something. They will almost certainly be doing this in assembler, and it could be quite a lot of code. So they will already know what they want to do. They will be able to look at these registers here and work it out for themselves. But the fact that we've actually covered it to some degree is quite useful. So what will happen if we go and have a look at the modes? Sorry, the GPIO interrupts. It tells you how to do it. Or basically, you need a vector for it to go. So when the event takes place, it has to shoot off and get an address from a vector address, and then go off to a service routine. So it's probably likely that there's quite a lot of work would be going on if you were going to do something on those edges, but it's quite versatile. I think it's quite a good bit of kit, really. You might have a special protocol that you need to write a driver for a special protocol, like a module that you want to put in if you're communicating with some odd device. So I can see how that could be quite useful. So I think that brings the video to a conclusion, and I hope you've enjoyed it, and I hope you found it useful. I learnt a few things while I was doing it, I must admit, so it's quite good for me. That being said, like and subscribe, you know the drill. It all helps to make the channel grow. We are not growing fast, we are growing slowly, so these videos take a long time, and really appreciate your help if you would subscribe. And that being said, I will see you next time.